Hello and welcome everyone. In this day 31 learnings of graphs, we have looked at graph introduction with graph basics and representation, graph traversals with BFS and DFS way of traversing a graph. Now we are in a third session of graphs learning with MST and Shortest Path algorithm, right? So one thing that we should understand is graphs is one of the most uh, practical possible data structure. When I say that, so we can take an example in our daily life, such as uh, so finding a shortest path is a graph based example, like uh, finding a distance between two cities with multiple routes. That's one example of graphs. And finding a minimum possible uh, route, a flight route, is also another example. And there might be many practical examples, but these are the few things that we can think about, right? So let's understand shortest path algorithms based on different types. So as I said, examples might be distance between. So here, vertex or node might be a city, and a distance connecting two cities might be, or we can assume it as an edge, right? So similarly, we can have another example, which is another. So these are two basic examples that I can think about, right? So yeah, let's um, start thinking on examples that, or the variations that we have in shortest path algorithm. So we can have a graph with unweighted graph. So in this case, we can simply assume all edges to be value 1. And in case of weighted graph, there can be of two types. One, all positive edges. This can be uh, one scenario, and in another case, mix of positive and negative edges. Yeah, so there are algorithms to solve all of these. So first thing is, this one can be solved with uh, BFS or some basic modifications to BFS, a simple first traversal which uses a queue type data structure. Um, we push in top element, and we also explore each of the neighboring elements, and we explore the shortest path between two uh, nodes or vertices. Similarly, here for positive edges, there is Dijkstra's algorithm. All of these I have covered it in common algorithms playlist. But in this video, I will be having to take a quick walkthrough on the code and also the idea behind how Dijkstra's algorithm works for having to find a shortest path between two positive edges, or a source node and a destination node with edges in the graph being positive, or no, edges in the graph being positive. And this one is Bellman Ford's algorithm. So these are the two things. Let's talk about first variation, which is of unweighted shortest path algorithm in a graph. So let's so let's consider a graph something like this. Consider this as a social networking site where these are uh, friends who are connected as a first level and second level and so on. So five, six, 8, 9, and 7. So consider it this way, right? So 6 is also connected to 8, and 5 is connected to 8, while 3 is also connected to 6. Okay, consider this one where we have this kind of graph. Consider this something like a social networking graph. So let's say we ask a person 0, who are your primary friends? So he can say 1, 3 are his primary friends. Similarly, for 3, 0 and 4 and 7 and 6 and 5. These are his primary friends. So let's say we want to know 0, how is he connected to 6? So he is a mutual friend or second degree friend to 0. And similarly, if we want to know the relation between 0 and 3, we should say he is a third degree friend who is associated with 5. 5 is also associated as a friend to 3, right? So that's the kind of relationship this can be, right? So the code, the way that we are going to implement BFS here would be, uh, we are going to be having a simple BFS algorithm. Here would be, we are starting out with a while loop. If q has an element, then we dequeue it and we go through all the neighboring elements, all the edges of the particular element, pq and element, and for neighboring nodes, per nodes, we check if infinity, distance is infinity, then we update a distance array. Distance array is number of nodes, and initially and all initially will be infinity. This is the value. And next we will also be having a previous array, which will be an array of n nodes filled with -1. So this is helpful to get a relationship between a specific node and a third degree relationship like we talked about. So if this is infinity, we update distance to +1 with the element node. So this is our logic. Let me quickly switch to JS bin editor and let's walk through the code. Right? So yeah, switching to JS bin editor. Yeah. So this is the specific graph that we have, and consider this as a social networking site with degrees of separation. So let's say 0 is you, 1 to 4 are all your friends, and 5 to 7 are friends of friends, and 8 and 9 are maybe target friends, right? So this is a graph that is built this way, and so there are about 10 vertices or 10 nodes here, and let's understand what is the specific. So yeah, unweighted, okay, unweighted social network is the function. Let's yeah. So this is the BFS function that helps us calculate a shortest path with a graph and a source which is provided. So we are going to have a distance array which would be helpful to calculate distance from a source node to all the other nodes, right? uh, Either a primary or a secondary or a tertiary level deep. So we firstly started off with a source node, and we also set the distance to the source node as 0, and we start a while loop with initially having source node, and we explore all the edges and the neighboring nodes connecting to the source node to the uh, neighboring nodes with an edge. So these edge, so initially these edge would be marked as infinity as you see here, and we update these neighboring nodes with current node, which is, let's say, initially source node, and we update it to 1, and we update the previous node to the current node, saying that this is an origin place, right? So let's say in this case, if we switch back to drawing board, so let me take this in a new page. Okay, so at simple dry run, understanding the way that we can do is, let's say we start out with node 0 in step 1, and we explore 1 and 3, and distance arrays would be updated to distance of uh, 0, 1 and 1, and all others infinity, and previous value for these will be -1, 0, 0, right? Step 2 would look like since we have explored 1 and also we have explored 3, we also need to push in the related neighboring nodes to 1, which is 2, and for 3 there are multiple neighboring nodes starting from 4, 5, 6, 7. So once we do this, our array gets, once we explore all of these elements, 0 will be -1, this will be 1 will be 1 and 0, and 2 will be, the element 2 will take up a value of 2 and a 1, and 3 will have 1 and origin of 0. This is distance and previous array. So this is how it would look: 0, 1, 2, 3, 1, 2, 3, and for fourth one, coming to fourth one, we can say fourth one is introduced from 3, so it will take up a value of 2. Since 3 is connected to 4, that's the path that pushed this specific 4 in. So this will take up 2, 0 to 3 and 4, and the origin will be 3. That's the shortest path. And 2 will also, once we explore 2, we will still have 4, but since this would be explored and it will be having a distance, we will still keep the first occurrence or the first shortest path occurrence. So that's the way that this goes, right? Similarly, all the specific nodes in this array will be explored, and it will only calculate for unique set of nodes which doesn't have distance. Once the distance is calculated, it will be a shortest value. That's something that the algorithm takes care of, right? So with this understanding, uh, I will again switch to JSPin. Here, as I said, this is a condition which checks for if a node is visited or no as well. So we return distance and previous array, which answers us few questions like, here we have this. So we can get a degree of separation with 8 as 3, right? Which means 0, 1, 0 to 3, 3 to 5, and 8. 1, 2, 3. 3 are the edges. 3 is a weighted value to reach the node 8 from 0. So yeah, something like this we have a BFS algorithm. So next we will quickly switch to a new page, and we will also start with Dijkstra's algorithm for a positive values only weighted graph. This is scenario 1. This is scenario 1. We are not going to talk about scenario 2, which combines both positive and negative values. There is Bellman-Ford's algorithm, which I will upload in near future in the common algorithm playlist. Right now we will talk about Dijkstra's algorithm, which I already have discussed in my common algorithm. I'll just go with a code walkthrough and how the algorithm works in a brief way, just to keep this video minimal and very short in duration. So yeah, let's take an example. Okay, so let me draw out an example. So let's say we have 0th node going to node 2 and 5. Here's 1 and here's let's consider this way. So and one connects to two, two connects to two, five. So weight of these edges would be 40, 200, and 50, and 100, and 150, and 150. Okay, so let's say if we are asked to find a destination node starting from 0 to 3 or 4, what would be the lowest value, right? So we would say 0 to 1, 1 to 2, 2 to 3, because we see out of any of these, 200 is higher than having to take this route, which is 0 to 1, 1 to 2, and either 3 or 4, right? Because 0 to 1 takes 50, 1 to 2 takes 100, while 0 to 2 alone takes 200, right? So in such weighted problems, we consider a similar approach, which is a similar approach to what BFS had been modified to. We would be using Dijkstra's algorithm, which is slightly similar to BFS, but we would be starting to use a priority queue, uh, which starts out, let's say, at a source node 0, and we would be having a while loop, which until all the not empty, and we continue, we dequeue, and we check if it's visited, we continue, else we mark it as visited, and we, for any specific node, we always calculate a minimum value, right? Like for example, in this case, let's say 0 has connected nodes of 1, 2, and 5. So the minimum value that we would be, the minimum edge will always be considered with priority queue, which is 50, and similarly here it would be 200, and it would be 40, right? So all of these will be updated. 40 will be considered first to travel from 0 to 5, but we at the eventually we are looking to calculate 0 to 3 or 4. So next will be 0 to 1 will be 50, and 0 to 2 will be 200, and next one, we once we push this to priority queue, once we explore these these elements 1, 2, and 5, we also push their connecting neighbors, which is 2, and 1 has 2, and again 2 will have 3 and 4. 5 doesn't have any neighboring node. So yeah, in this second iteration or second step, we also would evaluate the lowest possible value, which is we would figure out that it is not 0 to 2 edge, it is 0 to 1 and 1 to 2 edge, which helps us provide a shortest path. So we will see that, but let me draw out an uh, algorithmic steps for these. So we would also have for loop with edge, all the edges of the current node, and we check if minimum distance is less than distance of neighbor, then we update it. So then update. So similarly here in this case, we check minimum distance, which helps us update if there are any possible routes to a specific node that gets updated. So yeah, so that's one thing. Yeah, maybe I will switch to JSPin editor. We will quickly go through the code and we will quickly understand. But please do look into uh, common algorithms playlist where I've explained Dijkstra's in detail. So yeah, let me switch to JSPin and let me quickly walk through the code that we have. So consider this as a graph, and this to be a network of flights between cities, and we are looking to explore the shortest path or the cheapest flight cost from NYC and route to Miami or Seattle. So Miami or Seattle, 1, 2, 3, 1, 2, 3, or 1, 2, and 4. So that's the shortest path, right? And flight cost is as defined here. 0 to 1 takes 1, 1 to 2, 0 to 2 takes 150. That's the shortest path. 0 to 3 it takes 300. 0 to 4 takes same 300, and 0 to 5 takes 40. Right? So that's the shortest path. So the algorithm to understand here is something like this. I've even added all the comments just to understand this better. So we would have similar visited, distance array, and previous array. Here we would also have visited array, and we see priority queue which starts from the source node 0, and we also push the source node with distance 0, and we explore all the edges, and if it's already visited marked as true, then we ignore it. So if new distance, which is distance of neighboring node, then we update it with the distance value and also the previous node path, right? So yeah, this is a crucial logic. Yeah, something similar I have. You might see the code slightly different, but this might be the uh, standard kind of way of implementing text, right? So just go through my common algorithms digress video playlist as well, right? With this I will stop. Let's go to the last one, which is unweighted. uh, so it would be weighted shortest paths. uh, so I don't think so I picked it up here, so let me see if I. So I have not added the algorithm here. Please expect Bellman's 4 algorithm to be coming soon in my common algorithms playlist. Bellman 4's algorithm will help us in finding uh, shortest path for edges which are of positive or negative values, right? So with that, I will quickly switch to drawing board where we will quickly talk about MST and we will close this video out. So MST stands for minimum spanning tree. Uh, Spanning tree, which means, let's say we have an example uh, tree, something like this: A connecting to B connecting to C connecting to D, and 2, 2, 3, 2. So let's say if we are asked to find a shortest path between A and D, A to D, then we say A to C, C to D, right? In case of MST, it would. In case of MST simply means uh, we are required to establish edges to all vertices with a minimum possible weight of the total edges after picking out the minimum edges that connects between all the vertices. Like for example, A has the shortest edge with B, which is 2, and similarly B has the shortest edge to C, which is 2, and C has a shortest vertex to D. So we altogether ignore this edge since this has a more weightage. So if you see, this graph had a weight of 3, 5, and 9. Here we simply have a weight of 3. And you should also observe the number of vertices or edges here where 1, 2, 3, and 4. Here where 1, 2, and 3, right? And edges were this one and vertices were 4, which indirectly means a minus value of 1. So that's about MST. So MST examples for MST means establishing network cable to all homes in city with minimal cables and length. So this is the example. So there are two algorithms. Prim's algorithm is one that I've already uploaded in common algorithm playlist. I will just talk about it. So it also has an implementation of priority queue where each element is going to be checked with minimum value, minimum edge, and all of the edges would be explored. All of the nodes would be explored with a specific edge, and all of the vertices will be marked as visited. And that's the way that Prim's algorithm work. I will not even add anything here. I will quickly take you through the JS bin and walk through the code to this one. But let's quickly understand how Prim's algorithm is. So here I've even added a lot of detailed comments here. So as I said, priority queue, there would be a priority queue which always gives us the minimum set of value, and we check uh, if this was already added to MST and it's already visited, then we ignore, else we say this is visited and we find all the edges and we check if it's not there in the neighboring node and its edge weight is less than minimum weight edge weight of any of the neighboring nodes, then we consider it and we add it to the minimum edge weight array that we have here, and that's the value that we also return at the end. So something like this would be of Prim's algorithm. Yeah, I will stop this video since it's exceeding quite a bit of duration. Please do go through my common algorithms playlist, and please do post any thoughts or any doubts in the comment section. With this, we will be stopping learning with graphs, and next we will be starting with a new set of uh, algorithms, maybe with sorting and searching kind of things. Right? This would be a little lesser intense. Okay. Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.